Have you ever wondered how manufacturers decide the dimensions of their packaging? It isn't random. By using calculus, we can find the exact dimensions that maximize the space inside a container while using the same amount of material. This process is called optimization, and today we will master the steps to solve these problems from scratch. Optimization is used in engineering, logistics, and economics. Whether you are building a fuel tank or a cereal box, the goal is usually to maximize volume or minimize cost. In this lesson, we will focus on the geometry and calculus needed to find that sweet spot where our volume function reaches its highest value. Before we dive in, remember that the derivative of a function represents its rate of change. When a smooth curve reaches its maximum or minimum, the slope of the tangent line is 0. This means we can find optimal points by setting the first derivative of our volume equation to 0 and solving for our variable. To optimize volume, we must first understand the geometric constraints. For a standard box, the volume is length times width times height. In most problems, these dimensions will be related to a single variable, such as the size of the corner we cut out of a flat sheet of material. Imagine we have a flat sheet of cardboard measuring 20 cm by 15 cm. We want to create an open-top box by cutting equal squares of side x from each corner and folding up the sides. Our first task is to express the dimensions of the resulting box in terms of this unknown value x. When we cut two squares of length x from the 20 cm side, the remaining length is 20 minus 2x. Similarly, the width becomes 15 minus 2x. When we fold the flaps up, the height of the box is exactly x. We now have all three dimensions defined by a single variable, which is crucial for calculus. Now we multiply our dimensions to get the volume function. V of x equals x times 20 minus 2x times 15 minus 2x. After expanding the polynomial, we get for x cubed minus 70x squared plus 300x. This cubic function represents the volume for any given cut size Ex. Our goal is to find the value of x that makes V as large as possible. Every physical problem has constraints. Since lengths cannot be negative, x must be greater than 0. Also, since our shortest side is 15 cm, we cannot cut more than 7.5 cm from each side, or we'd have no material left. Our domain for x is strictly between 0 and 7.5. To find the maximum, we take the derivative of our volume function. The derivative v' of x is 12x squared minus 140x plus 300. We set this equal to 0 to find the critical points. This is a quadratic equation, which we can solve using the quadratic formula to find the specific values of x where the volume stops increasing and starts decreasing. Applying the quadratic formula gives us two solutions, approximately 2.83 and 8.83. However, remember our domain constraint. Since x must be less than 7.5, we must reject 8.83. This leaves us with x equals 2.83 cm as our only viable candidate for the maximum volume cut. To confirm this is a maximum and not a minimum, we use the second derivative test. V" is 24x minus 140. Plugging in 2.83 results in a negative value. In calculus, a negative second derivative means the graph is concave down, confirming that our critical point is indeed a local maximum. Finally, we calculate the maximum volume by plugging 2.83 back into our original volume equation. The resulting dimensions are roughly 14.3 by 9.3 by 2.8 centimeters. This gives us a maximum volume of approximately 379 cubic centimeters. Any other cut size would result in a smaller box. Visualizing the function helps verify our work. Notice how the volume starts at 0 when the cut is 0, rises to a peak at 2.83, and then falls back to 0 at 7.5. The peak represents the most efficient use of our material for maximum storage capacity. Let's look at a different shape, a soda can. Suppose we have a fixed amount of aluminum and want to maximize the volume. Here, our constraint is the surface area. We have two variables, r and h, but we need to express one in terms of the other to use calculus. By rearranging the surface area formula to solve for height, we can substitute it into the volume formula for a cylinder. This gives us a volume function that depends only on the radius. Now, we are ready to take the derivative with respect to R and find the optimal dimensions for any can. Interestingly, when you solve this optimization, you find that the maximum volume for a given surface area occurs when the height is exactly equal to the diameter. This is why many industrial storage tanks look a square from a side profile. It is the most mathematically efficient shape for a cylinder. What if the box has no lid? This changes our constraint equation. In optimization, always read the problem carefully to see if all sides are included. Removing the top side shifts the critical point, meaning a taller box might become more efficient than one with a lid. A common mistake is confusing the objective function with the constraint. The objective is what you are trying to maximize, in this case, volume. The constraint is the physical limit, like the size of the paper or the amount of metal. Always differentiate the objective, not the constraint. Don't forget units. If your dimensions are in centimeters, your volume must be in cubic centimeters. If you are given a volume in liters but dimensions in meters, you must convert them to a consistent scale before you begin your calculus operations. While the maximum is usually at a critical point where the derivative is zero, always check your endpoints. In some advanced problems, the best solution might be at the very edge of what is physically possible. In our box example, the endpoints resulted in zero volume, so the critical point was the winner. To wrap up, the optimization process is a reliable 6-step method. Start with a visual, define your formulas, reduce them to one variable, find the derivative, solve for your critical points, and finally, verify your results using the second derivative test or the context of the problem. The power of calculus is that it turns geometric intuition into precise numerical answers. By finding where the rate of change is zero, we find the peak of efficiency. This allows us to design better products and understand the mathematical limits of the physical world. Try this on your own. If you have a 10 by 10 square sheet, what is the volume function? Following our steps, the length and width would both be 10 minus 2x, and the height would be x. Expanding this will give you a cubic function ready for differentiation. Can you find the x that maximizes it? The derivative for that practice problem is 12x squared minus 80x plus 100. Setting it to 0 gives an optimal cut of 5/3, or about 1.67. This demonstrates that the same logic applies regardless of the initial dimensions of your material. You now have the tools to optimize any container. Thank you for exploring the intersection of geometry and calculus with us. With these optimization techniques, you can solve complex real-world problems with mathematical certainty. Keep practicing, and you'll see these patterns everywhere in engineering and design. Generated by Vision Solve AI.